All right. Hmm. My connection seems to be a little spotty. Let's see what's going on here. All right. Okay, sorry that took so long. I was just checking to see about getting this camera to work, and uh, it doesn't really look like it is doing very well. Huh. Well, we'll see. We'll see how this streams. If it gets a little laggy or anything, please let me know. Hopefully, this isn't going to be completely horrible. I don't think it will be, though. We'll see. If it gets to be bad, just throw something in the chat and we'll take it from there. So, I am starting this off a little different, where I'm putting just for this one session, I'm going to be stopping that to do app we're working on because I've been playing with some stuff. I've been working on a small video series that will, how would you say, basically, I just go through, I've been reading, going over and over these books, Category Theory, A Gentle Introduction, some like old books from the 60s, like these on like finite mathematics and things like that. Of course, the category theory for the sciences, all that stuff. A couple other books. I've just been going through, and one of the things that I found kind of, well, not weird, but I couldn't really find a lot of resources that like turned all of those diagrams and all those laws and axioms and all that into like JavaScript examples. So I'm just putting together my little explanations. But going through and like reading these, well, two things. One thing is I need a way to represent this stuff in JavaScript. So I'm just going to kind of go over this thing I've been working on. It's mostly for demonstration purposes, but it's kind of cool and fun. So it's more just a nerding out, playing with functions and sets and creating sets and doing all that. So it makes it real easy to explain a lot of that early stuff on set. But going back and looking through it, like there's certain things I skimmed over as a JavaScript developer, right? Like, what do I really care about the pre-image of a function, right? Like, I made sure I kind of understood it a little bit, enough to understand like what it was saying, like an image of something. It basically an image of a function is all of the attributes that have been mapped by like their input sources. So in programming, that I never really thought, "Ooh, that's a big deal." So I'd never really played with that or like thought of the implications of those laws and rules other than how they pertain to other aspects, more abstract aspects. Also things like, pre-image, like who cares about pre-images, right? Like I don't really care if, and what a pre-image is, so I could do a pre-image of a function f that, like say it's something that goes from string to Boolean. I could do the pre-image of that function on Boolean or on true, like one element, and it'll give me all of the, how would you say? I'm not even talking into the camera. Good thing I have this. But it would give me all of the inputs that correspond to like true, right? So any input from that other set, it would correspond to whatever is true. So everything that's sent to true, basically. And I never really, because in programming, I never really thought about that. Like I'm mostly thinking, how do I get an email record out of the database and check it against a JWT, right? Like I never really thought about like the implications of that and like how the image of a composed function like translates through the other sets as they go through. So you get like a flashlight that shines through on the elements that are hit in the mappings. So it's really hard to relate that to like getting the email from a JWT. That's how I say it. I don't like JWT. I do JWT. Drives people at work crazy or bananas. So I don't know. So as I'm going through and putting these lessons together, I needed ways to explain this. And then I started like really thinking about like how you could use things like that for classification. So instead of a function transforming a value, you could use it to be a classifier or something that just maps into another function. And then you could build like this set of functions, or I'm sorry, a set of values inside of that other element or inside of that other set that can be classified by like what their results are. And you can even put them in orders and things like that. So as I started playing, it still, I don't know if it's really given me too much something, how would you say? I don't think it's really given me something that I could take and apply in my everyday, pull this email and check it against a JWT. Like, but what it does do, like knowing about that periscoping, it really lets me think about getting coverage on my functions, right? Because if I understand how a function will flow through and how inputs will map to their outputs, I might be writing a bunch of needless functions whenever I really need to only cover a set of, or a small set of the results based on the inputs that are getting to there. So it's just things like that. Hey Yuri, how are you doing? Yuri says, greetings, Ian. So anyway, these are just things that I've been running into, and it's been kind of blowing my mind because as I was going through these books, I never really, I mean, I did the exercises, I would do all the things like that. But I went back and really just started diagramming everything out and trying things like what happens if I take a 3-element set into a 4-element set. What does that mean? What does it mean for something to be injective? Like how's the cardinality of a set, or how the cardinalities of the set relate to it being like an injective function? Like, because there's sometimes you can't have an injective function based on the lengths of your source and your target. But anyway, so the other thing that it brought up for me is I've been thinking about JavaScript all wrong. Well, me personally. So while we put in these types, like say I have a function, that goes from string to, let's say, number. Really, in JavaScript, because we don't have a language, all these really, or I'm sorry, we do have a language. Since we don't have like strong typing and whatever available to us, we're not really saying a function from a string to a number. There's really this type called JavaScript, which is every single value that could be represented. And we're really bringing functions from JavaScript to JavaScript. And it really only matters in like inside of our functions, how they, how would you say, how we build subsets of valid types, I guess you would say. So I've never really thought of just JavaScript as one big set and these just being subsets of this. It kind of makes things lay out kind of neat. But again, it's really hard to like go through these functions if we're just going from one type to another type to another type. So I got to thinking about sets and like different ways to represent sets. So first thing we'll do, let's just jump right into it. We got enough people watching now. Is I would like, and the thing I'm about to build, I have a really hard time calling it a functor. And that's because I'm having some issues doing the proof on composition. But let's just, for now, I'm not going to call this a functor, but I'm going to call it a context. So in order to get this to work, we need to have a context of that we can safely run valid JavaScript in, right? So if we have this context, we'll just call it define set. We'll make this thing that will take any object or any element and be able to make this subset from that one big type of JavaScript, right? That's all we're really doing with this, is we're defining other subsets of the big thing JavaScript, right? So let's do something called define set. And let's bring in Curry, and we'll bring Curry in from Crocs. Okay, and we're not building anything in the front end, so we're just gonna bring in all of Crocs. Why not? We should probably spell require a little bit better. Sorry for my horrible explanation. I'm not good at explaining like what we're about to do, but hopefully the code will help. So what we want to do is there's two ways to define a set, right? So defining a set. There are two ways of describing, I don't know, we'll just grab this first one, right? Not? Why not? There's two ways of describing members on the set. One is this, where I call it membership clauses. You basically define from all the elements of everything, you basically define a membership clause. We're not going to do that one first. And by the way, I keep getting that my health is bad. Is there like glitches and stuff in the matrix? Is there like lag or anything like that? If so, please let me know in the chat. All right, so there's two different ways to define a set, right? So one way that's by extension will be the first one that we look at. Basically, this is just giving something a label. Like, say I have a 2-element set. I can make that a Boolean. Okay, it's not, so this is doing some buffering. I'm going to shut off the camera for now. I don't know if that is causing the problem, but let me shut this off and we'll see if that helps. Sorry about that. Okay. So what we're going to do is think about a way to define, how would you say, this way of defining a set or describing a set. Remember, there's two ways to do it. So what we want to do is we'll create a function called define set. And we're going to take in something that we'll call query, right? And we will take in some sort of x. And this will be kind of a function. You'll see how we use it. So the first thing we want to do is see if this is an array. Because we're going to define things like this. Const, and let's say a is equal to define set, and say that a is a, we'll just give them the labels a and b, right? So that's all that a is. So we'll just come into here and we'll do query, and if it is that, if it is an array, then we also want to return true if we'll say query dot includes, and we'll say x. Okay, so now we need to bring in is array, and we'll do that here. Is array, and Bob's your uncle. So now we have this thing called a, right? So let's go ahead, and now that we have that set a, we'll change this log here to be log, it's log. We'll do a, and then we'll pass in a. But we need to do something with this, right? We need to do something with this value. So we say that if it is a member of this set, if it's actually included as one of the labels, we're just going to return x. And we're going to wrap it in an array. Otherwise, we're not. Okay? So when we call a, we can now, do that. If we put b in, we get back b. But if, say, we put it undefined, we get nothing back. If we put in 1, 2, 3, we get nothing back, right? So now we have a way of defining a set with labels. So we can do neat things with this. So now that we have that, actually, let's do this. We'll make something called helpers, and inside of helpers, we'll move this, and we will move this. Okay, and then here we just want to module.export, and this will be define set. All right. So now we have a way to define labeled sets. as long as we pass in an array for that defined set. Let's do this. Get rid of that. And then here we'll do const define. We can close this now. We'll do define. Oh, come on. We'll do define set, and we'll pull that off of helpers. Let's not call that helpers. Let's call this, we'll move that to sets. All right. Okay, and at any time, if it starts getting weird or you're curious about something, oh my gosh, what are you doing here? Go ahead and interrupt me. I don't mind, just throw something in the chat. It's fun. All right, so now we have this. We'll call that sets, and we need to bring sets in, and we will just bring in sets. Okay, and modules dot exports. Okay, now we're good. All right, so now if we call that with a, if we call it with for, if we call it with null, we now have a way to check for, at least on one end for an object, to check to see if an element that we're pulling out of values in JavaScript is actually part of this set. Okay, and we do it like that with these labels. So these labels can be numbers or strings. You'll see why. It just makes it easier for defining mappings or things like that, right? So let's make another set here. And one of the things that we like to do with sets, right, is we like to combine them in some way. So maybe we want to union these. And union is basically just plus, right? Like it's a coproduct. So if you think about a union between sets, you're taking set A and set B, and now you have a set AB, which is the combination of both of them, right? So you make it larger by combining the two. It's the same way that, maybe and either work. It's the same way. It's basically disjunction, right? And I'll show you what I mean by that. So now that we have these two sets, let's just make this one, and we'll just make sure it works. Delete to this and that. We'll do 1 and 2. Okay, and that's B. So now if we throw B in there and we put that in and we put in 1, it'll return 1. 2 returns 2. Bam, this part is super easy. An object returns nothing, right? So now let's check out what conjunction or a intersect. Let's do a union. So we want to add both of them together. So a union, as we know, is a disjunction. So we'll go define union. And we just come over here and query. So we're going to need 2 of these sets, right? We need 2 of these defined sets. And to do that, we'll take A and B. Those are the 2 sets, and we're going to need to take an X because we always have to compare or lift a value into it, right? Always have to lift that value into our neat little context that only allows valid JavaScript to run. So now what we want to do is, because this is going to give back an array, and we always make sure that inside of our context is an array, all we need to do is check the length of A. Hey, kitten. What are you doing? And we want to check the length of B on X. So, I'm sorry. Like I said, this is intersection. So this is a union that we want to do. So union is or. It's a disjunction. So now if this is true, then we want to return, what do we want to return? We want to return X, or we don't want to return anything, right? So now we have define union, and this is probably wrong, but we'll see. And now we can get a union of these sets, hopefully, if everything works out. So B will not allow an A, right? So that does not allow an A. But if I take the union of these, define union, and we will do const AB is equal to define union. All right, and then we'll take that of A and B. So now we have AB. So if I call this with AB, we get back an A because it's now the union of those two sets. And I'll get it for A, AB. I'll get it for 2. Oops. I'll get it for 2. And if I put anything else in, like a blank string, or undefined, or null, or anything else that is not part of that set, I just get back nothing because it's invalid. I took it from, and what I mean by taking it from the type of JavaScript, so say I have let, and we'll call something x equal to 1, 2, 3, right? So if I were to log x, right, I get 1, 2, 3. But later on, I could come through and say this is actually a string. Like this isn't set to any type. It just comes from JavaScript, right? It comes from the type of JavaScript. And we'll just do now is equal to x. So now it's a string, right? So what we're able to do is move any element from the type of JavaScript and then check it to see if it's a member of a set. So this allows us to move objects. So here we're really defining, how would you say, well, we're defining a type or an object. I guess you could call it an object in a, we'll just call it a set. We're defining sets. All right. So now there's another way to define these, and this is having a clause of membership, right? So one of the things you'll notice about this clause of membership, a set whose members are the first 4 positive integers. So that's basically a question. We're asking for any element that you give me from the whole world and the whole universe, is this one of the first 4 positive integers? Or we could take all of everything in the whole world and have strings that represent the French flag, right? So we're basically asking a question to say, hey, is there membership to these, right? Like, does this have membership? So to do that, since we're just asking questions, this is basically just a predicate, right? Like it's just us running a predicate function. So let's go ahead and change this a little bit. So we'll put one of these in and we'll say is function, because we want to also be able to define these the other way, where you're actually asking a question, right? So we'll say is function query. And here we'll do or. Okay. And let's do some of this and delete to the end of that and just paste that right in. We're basically going to keep that. Boy, this resolution sure is something, isn't it? We'll do is function. What's a better way to write this? I don't know. So we also want to then check if it is a function that it takes that query and runs it against X. So if that returns true, that'll get us a predicate that will ask the question of whether or not this thing belongs, right? And I guess the other thing we could show is intersection, because intersection is basically, we'll get to that. All right, so here we have this. It's this defined set. Let's see what happens if I do this. Okay. It's not that good, but whatever. This is what we have. Okay, so we'll basically say, is this a function? If it is, go ahead and run the query against it. And if that becomes true, The other false will just fall right through, right? Because a function is not an array. Anyway, basically this will fall out just fine. Fall out, boy. So then what we're doing is checking if it's an array, then we do our array things. So now we can start asking questions about things, right? So for instance, maybe we want to constrict something to a, let's see, something that has a length. Okay, so what if we do const has length? Okay, so now we can do define set. And we'll take an x, and then we just check to see if x and x dot length. Okay, so we basically want to check to see if this has some sort of length to it, like whether it's empty or like, non-empty, or whether it could even be thought of as to have length. So now we have a set that if we pass it an empty array, we get nothing back. If we pass it something like that, we get nothing back. Because nope, hold on. Is function, and then query is x. Hold on. I did something silly. So if x, no. Hold on. Oh my goodness. How embarrassing is this? Okay, so we're saying if this is a function, we do our define set, we have define union. All right, so if this is a function, query, and query returns true. That should go through. Hold on. Goodness gracious. I'm like, yeah, check this out. This will be cool. But it's not that cool. All right, so let's do... Okay, now why is that not working? So if I take an x, I want to do if x hold on. Oh. Oh my goodness, I didn't save it. All right, so basically we now have in the whole world of JavaScript, we now have a set that we've defined that will always give you back something that has length, right? So what if we want to define another union or something else that will return of all the things that could have length, something that is less than or equal to 3. So this will only return things back. And because 0 and all that, well, we'll see in a sec. All right. So because this is blank and doesn't have any length, it's not going to return back. But that will. So that's kind of strange too. Well, not really. Okay. So what we need to actually do is check to see, because we want it to match up. So we can do x dot length just for now. There's probably a much better way to do this. Is greater or equal to 0. Is greater than 0. And this is conjunction. Okay, so that comes back. This should come back. All right, but if I have anything that has length, it comes back as that, even as a string, because string actually has length to it, right? So we get back the string, we get back all of that stuff by making this membership clause. So say we want to only include strings that did this, then we can define a union of these two sets, right? So we will say define union. Well, let's do another define set. And we will say str, right? And we'll do define set. Define set. And then here we'll do is string, because now we can just ask those questions. We'll bring this in from const, let's say is string, and we'll bring this in from crocs. Okay, and there we go. Oops. Now we bring that in from crocs. So now we have this str, and we'll say length 3 here, length 3. And this includes everything that has a length that's between 1 and 3, basically. So that'll work. But if I have 1, 2, 3, 4, this doesn't go in there because it doesn't have a length of 3, right? This is empty, so it doesn't have a length. Right? Makes sense? So now let's create our union, and we'll do stir length 3. So now we can make a subset that is anything that's a stir just by going union type, or define union. And now we'll just do stir and length 3. So now we have this stir length 3, stir length. All right. Okay. But it's not a union that we want on here, because a union's going to include everything, any string, right? So this is a union that we have. So this is addition. What we really want is we want conjunction. We want to only include things where there's an intersection between them to actually get this to work. Sorry, my bad. So let's create define intersection, I guess. I don't know. That's probably not the right word. Oh, yeah, another disclaimer. I have no idea what I'm doing. I have no idea about math or anything like that. I just read a few books, and I play with JavaScript sometimes. So don't take anything I say with, take it with a grain of salt. I'm probably wrong about some of this, but all right. So for our intersection, we need an AB. It's basically the same thing, and we could probably abstract this later. And instead of conjunction, or instead of disjunction, we need conjunction. So now we have defined intersection. This will go above here, and we'll do intersection. Okay, so here we need to take define union off. So let's do some of this. All right, and we will do... all right. So here we want the intersection of these two sets. So it needs to be inclusive. Okay? So now that doesn't match, but 1, 2, 3 does, but not 1, 2, 3, 4, you know, because it doesn't have that. But watch what we did. We now took the arrays out of that. So say we have 1, 2, 3. This used to pass, and this would pass under length 3. But because, this would pass under length 3. But because we were able to find the intersection between these two sets, we were able to get that going. Anyway, so this is just one of the ways I was thinking about how we could actually represent set or sets and things like that inside of JavaScript to make it, I don't know, kind of match a little more to what the math's doing. But these are just some thoughts that I had. Feel free to berate me, things like that. This is just for the objects, right? Like this is just for the sets. We haven't even talked about functions yet because it gets crazy with functions. All right, so let's get into the functions part. What we need to do now is we want to be able to lift any JavaScript function into this nice little context that only runs safe things, okay? So let's get rid of all of this stuff. We don't need any of that. We don't need this for now. Let's actually, well, how should we do this? All right, let's do it this way. So we'll call this arrow, right? So we'll define an arrow. And how should we do this? All right, so what an arrow is we need a way to, because we need to move this into our little valid context or our little world where only valid JavaScript will run, we need a way to determine that our head and our tail of our arrow are actually checked, right? So we have this whole pattern going on where we have this, hey, if everything's good, throw it in the array, and hey, if everything's bad, just return nothing, you know, like we have that whole business going on right there. So we want to be able to account for that. And this might get a little gross, but who knows? We need to use our imagination with JavaScript, right? It's one of the fun things that we get to do with JavaScript. So let's have, we need two sets, okay? So we need an A and we need a B. And then after that, we need some sort of function to run over them, right? So when I'm thinking define arrow, let's just go ahead and bring it in here. Define arrow. So what I'm thinking is, say we have some set. We'll make a set A, which is equal to define set. And we'll just make this A, B, C. Okay? And then let's make a B that maps to, I don't know, D2. We'll make this map to 1, 2, 3, 4. Okay, so we have this A, and actually let's call this source, and let's call this target. Okay, so this is going to be our source of our arrow, and this is going to be the target of our arrow. So let's create some F, which is going to be define arrow. And what should this look like? So what we really want to do is pass S and T and then provide some sort of function. Now, one thing that you might have noticed, maybe, is if you follow anything with category theory or anything like this, if you squint really, really, really hard, we now have a function here that defines a HOM set or a mapping of a HOM set into our valid little area, like into our array, right? Because you'll see HOM set, like, or a HOM set in set would be, you know, like from some arbitrary object A to some arbitrary object B, right? Anyway, just again, you have to use your imagination with that. But anyway, and if you think about it, since it's only going to run functions that meet that criteria, I think it really does define an actual HOM set or something you can check to see if an actual function is valid. Anyway, So we have that define arrow, and then we want to have some sort of function, right? So it's really hard like to come up, one of the other things when I started making this video series that I noticed, it's really hard to come up with arbitrary functions, right, that do mappings. So let's take let's steal a little bit, since it's JavaScript, we'll steal a little bit from the object-oriented community, and let's create something called define map, right? So this will be define arrow. Okay. Right now, let's just do nothing. Let's just return the function just to make things work. All right, so we have that define arrow that will be curried and do everything like that. Let's do a define map. And what define map will do is, like I said, we're just going to steal the strategy pattern. Define map. We're going to steal this just straight up from object-oriented. Let's actually do a curry here. And then we'll do a map. And then we'll do an X. And all we do is just do map X. Right? So now we can define a mapping, right? That allows us to have an object that maps certain values to other things. So now we have define map defined. So that's good. So let's do, we'll call this general function, right? This is basically a general function. So the rules to a general function is, so since we have this S and T, hold on. Got to read it from a little board here. For all S belonging to S, so in this case, A, B, and C, there exists a T belonging to T, so that's either 1, 2, 3, or 4, where f of S is equal to T. Okay? So what that means is for every single one of these in source, if I were to run it through this f, given these two sets, I will always get back something from T, nothing outside of T. I will not ever get back nothing. And that happens for all of these. So for every A, I get something. When I pass B, I get something. When I pass C, I get something. And that's pretty much what a general function is, right? In order to be a function, it has to match those rules. Very, very important. So let's do define map. And what we're going to do is we have to have a one-to-one mapping, right? So we're going to say if I have an A, give me a 1. If I have a B, give me a 2 or a 3. If I have a C, give me a 6. Ah, that's wrong because there is no 6, but we'll play with that. We'll say give me a 2. So this will basically map A to 1, B to 3, and then C to 2. Okay, so let's go up here and we'll do define map. All right, now we have our general function. So here we want to pass in our general function. And now we have something that will do our type checking on both the head and the tail. And if it's valid on both sides after running through this function, then it's going to give us back the result of that function. Otherwise, we get nothing back because it's working in our little context of only run valid JavaScript, right? All right, so of course, that's not going to get us anything. It'll basically just return, when we do that, that gets us the function returned back to us. So what we want to do is return another function, right? And how we do this to define an arrow is we're going to have to do a little bit of this. So let's do const y is equal to, and remember, we're going to get back, this is kind of how we're going to do our little mapping, right? So we're going to take A, whatever A was, the type of A. We're going to take that. Let's call this source and target, actually. So we'll do S, and then this is the target, right? So here we'll do S, and then we're going to pass in our X. And then, if everything's good, we're going to map over it over our function. Okay? So remember, when we map with this function, it's going to take that function that we passed it and lift it into this context for us. Takes care of that. And then we're going to hit return. And what are we going to do? We want to check the length of this, because if it failed on the input, and do we really want to do that? Hold on. I think we might be able to get a little silly with this. Well, no, because we do need to run it through this. We may be able to do something, but let's just do it the quick and dirty way, right? So if we get a length back, we then want to return the result of passing y to our little bit there. So that's basically going to be our target. But we don't really want to pass the target. We want to take the value outside of that, right? Because it is inside of there. So we need to unwrap it, and we need to pass it to t to make sure everything's good. There's a pattern there. I'm not going to tell you what it is. I'm sure you can figure it out. But what we're going to do then is just unwrap it, and then we're going to pass it to t, returning the result of t. So now we get to check it on the back end to make sure that the tail matches, right? So now we have a function that can actually do mapping. So if we call f, and then we give back an f of a, we get our 1 because that maps to 1. If we come back here and we give it a b, we get back our 3. If we give it a d, because we don't have a d, that's invalid. It fails on that. Also, say let's give it a b, and let's say that our mapping was wrong. This is an invalid mapping, so the function does not match our rule that we said. This is now an invalid function, so it does not run. It's invalid. But now we can check the internals of a function. We can check all kinds of other stuff. Sort of. Because what happens if we lift a function that... so let's create a function that gives back a... what's the best way to do that? So if we could have a function, the other case in here, like where we'll run into problems, let's define, this is how you basically define a map, right? So anyway, before we get into that, let's just look at some of the things that we can learn from these, right? So one of the things that I've learned, like going through and watching all these, or like playing around, reading all these books and stuff like that, is, and I always skipped over this, but there's some important information when you say a function is injective versus surjective, right? Or neither. Like in this case, let's see. This is not a surjective function, but it is, hold on. All right. So if I have 1 and 2, or A, that'll give me something, and then C will give me something. So this is an injective function because every single one of them actually map to their own, a different target, right? They don't collapse or put anything in. So this is one thing that you can note about injective functions. So one of the neat things about injective functions like that I've learned is an injective function, in order to be injective, has to have a cardinality less than or equal, the source has to have a cardinality less than or equal that of the target. Otherwise, you can't have an injective function. So what I mean by that is, let's make the source greater than this, right? So let's say this is ABC, and we're going to map it into AB 1, 2, 3, right? So if I were to take A and then B, I need to map B to something, so I'll map B to 2, but I have a problem here because I can't be injective because both of these match up. Oh, I'm sorry. So for an injective function, for it to actually be injective, let me grab my board again. So an injective function for any t, or I'm sorry, for a t belonging to t, and for all S1 and S2 belonging to, S, if calling your function f on S1 is equal to S2, then that implies that S1 is equal to S2. So, and again, I'm not really, most of the video, like I go through and like write out that, like for the video series for this, and then show like how they map and then show it in here. But basically what that's saying is that for all of these, if I were to take a pair of two of them, if they map to the same location, they have to be equal. So like if A maps to 1, no matter what, A has to always map to 1, right? So that is, or anytime I get a 1 back, it has to be A. If that doesn't match, then I don't have an injective function, right? So injective functions are interesting when we start talking about isomorphisms or like bijections and stuff. I mean, they are kind of interesting because you know that they're not collapsing. Like if I can build subsets. They're basically an injective function is a way to build a subset of another set based on a function, right? So let's say I have 3, 4, 5, and 6. Right? And let's just say I have A and B. So I can create a subset of this just with the mapping. So it has to be A to B. And then we'll say that A goes to 5 and this goes to 6. Okay? So now if I put in B, I get back 6, and if I put in A, I get back 5, right? So what I really did is by using this mapping, all I did was use this function and this type to create a whole other subset. So now I could say that this mapping actually defines a subset of this set T, which is a new subset called 5 and 6, right? So that's one of the cool things about injective functions is you can use an injective function to create a subset of another function. And if I didn't take the time to actually play with this and do things like that, I never would have like seen things like that. But I don't know how that would apply to like getting an email out of a JWT or anything like that, but it's pretty cool. Like if you think about it, I can, instead of thinking as a function as one way to transform one value into something else, I could use that function to create whole new subsets. So anyway, it's just something to think about. I don't know why I went on and on. So that's an injective function. Now, there's other rules for a surjective function. So they call that an onto, right? Basically, I can map as long as everything is covered inside of my target, then it's a surjective function. So one of the things, so what that means is whenever I have this function, for all things in S, hold on, let me read the rule. Okay, so for all T belonging to T, there exists an S belonging to S where T is equal to f of S. So basically, that's saying for every single one in here, there has to be a mapping back. So immediately, again, just with that rule, we automatically know that the target, whenever we have a function that is surjective, has to be less than or equal to the source, the cardinality of it, right? So that's kind of cool because if it's not, then we won't be able to get full coverage on it. So we'll make this A, B, and C so you can see what a surjective function looks like, right? And then we'll make this So let's make a non-surjective function. So we can never, ever, between S and T have a true surjective function, because the cardinality of A, or the cardinality of S, is less than the cardinality of T. It needs to be the other way around. T has to be less than or equal to the cardinality of S, right? So in order for this to be onto, I would have to send each one of these to one of these. Now, to make it a surjective function, if I have that, like a 3 to 1, I could then do C, and C will go, this needs to go to 1. We'll say this goes to 1, and then we'll say that this goes to 2. So it's okay in a surjective function for everything to collapse, because the only thing that matters when something is surjective is that there's full coverage on the target. Every single one of those elements needs to be hit by one of the inputs, right? And that's what makes something surjective. So now, if you think about it, now you can use this information. So say I have a string, right? And I have a function that goes from all of the strings that could ever be in JavaScript down to, say the function is 2 uppercase, right? So is that a surjective or an injective function, or neither? And like you can think about that. I'm not going to tell you the answer, but I'll let you figure that out. So remember, an injective function is one that for every single S in S, there is a unique mapping to an element, or there is a mapping to a unique element in T, right? So that's injective. Surjective is that for every element in T, there has to be a path coming from an element in S, like when it does its mapping. So now if you use those, it's really interesting to see like how many things just really aren't surjective or injective, and they're a lot more rare than you would think. But you can also think of them as ways to get a subset, right? So if you think about that, and this I think will get us onto the next thing we need to do, which is composition, because we now need to compose all of these, and it would be nice to be able to compose all of our arrows, right? And what's my time looking like? So we're almost at an hour. So I didn't get to the equivalence stuff because I went on and on and on and on. But what I'm going to do is just show the composition. So we want to be able to compose these arrows. Okay, so let's do define compose. Oops. We'll do const compose arrows. Okay, and for composition, again, we're going to curry it just to make it real easy to use. We need to take a G and an F, so we can call F after G. And we also need to take a value or something to run in those, right? So at this point, like what F and G is going to be are arrows, so they automatically know how to hook up to each other. We got to do a little bit of finagling, but we'll make it pretty awesome, I think. Let's see here. So for this, we want to take a G, an F, and an X, right? So then we can do const. Oops. So we'll just do const Y because we have to do that wrapping and unwrapping and things like that. Because remember, we pass a value into this. Oops. We pass a value into G, which is one of these sets, and it's going to give us back the array, right? So now this will go through and has been validated on either part. So now I can do map. So if there was an error or something inside of that function, or if the first one, like going through G, failed in any way, shape, or form, we would get back an empty list. So then I just take map and I map that over F, or I map F under that. So there's that. We want to do Y is equal, right? So now we want to do the same thing that we're always doing. We'll do y.length. And if y.length, then we need to unwrap it because we're nested at this point, right? Because we have an array inside of an array. And we want to take that for, it's kind of like a chain, Kleisli arrow. Kind of. I don't want to say functor. I can't prove functor yet. So, I mean, it's basically a maybe, but I'm just having a hard time figuring out a way to come up with something that meets the proof. But anyway, we either unwrap it or we give back an empty, right? Because if there is no length, then everything's pretty much failed, things like that. We could give back the y, but hey, why not? We'll just do it this way. All right, so now let's just do compose arrows. And that will get those arrows out, and we'll do compose arrows. So let's create something, I guess, just to see how this composition of arrows works, right? And we also want to be able to lift compositions from JavaScript into here, which this is where I have a hard time proving this is a functor. And hold on one mo, I got to let this cat out real quick. It is driving me bananas. One moment. My goodness, that is a stubborn kitty. I am so sorry about that. All right, so let's define, we need to now define some sets. So let's define, let's just do some normal JavaScript stuff. We'll define a string, and let's define a Boolean, right? All right, so we'll do define set, and this will be is string, and we'll bring in every string. Okay, and then we need to bring that in const, and we'll do is string. Okay, is equal to require, and we'll just bring that in from Crocs. All right, so now we have this string that defines a set that defines strings. Let's make one, and actually we need to call it str. And here we'll do bool. And we'll do is Boolean. Okay, and here we need to bring in is Boolean. All right. All right, so now we have these two sets defined. We can now pull from, so if we have str and we put in a blank string, we're still good. If we do this, we're still good. But if we put in true, a Boolean, we're not good. But in bool, if we do that, we're good. And here, if we put in a string, we are not so good. Okay, makes sense? So now we have these two sets defined. We need to write some functions now. So let's take a function. What would be an exciting one? So let's actually, let's see. So we could take that string. So if it's a Boolean, so let's do this. We'll do const, and we'll go Boolean to, or no, what will we say? We'll say loud. I don't know, let's call it fn. So we'll define, let's call it f. So we'll define arrow, and this will be an arrow that goes from Boolean to string. Okay, and this is basically just going to be a function that goes x and will return true. And if not, we'll return false. Okay, so now we have f, and if we come into f and we send f this, we'll get nothing back. If we do this, we'll get true back. If we do false, we get false back. If we put in null, we get nothing, right? So now we have a function that will go from Boolean to string, defines that arrow. We don't need this open anymore. I think that's the last thing that we're going to define in there. All right, so that's what we have back. So now let's see about composing this, and let's create a union here. Well, let's just say, let's do that length. Let's just do a len3. So this will take an x. Nope. Let's do upper string. So we'll define a set that is a string. So we'll do and is string. And actually, we can do this since we're doing that. We can do the intersection. Define intersection. No. Nope, this needs to be a string. Sorry. So we're going to do define set. And we're going to check and is string. And then we'll check that x dot length is greater than or equal to, or sorry, less than or equal to 3. All right, we need to bring and in. And we'll just bring that in from Crocs. This is a little silly being so long. All right, so now we have that, we have that. That'll get us our upper string. So now let's create a function g. And we'll call g after f, which will basically take a string to an upper string, right? And what we want to do on this is call to upper. Okay, so now we should be able to do a composition. So we have these functions, they're lifted inside of there, everything's great, everybody loves it, especially that guy. So let's create a function called comp, which is going to be the composition of f and g. So we could probably call this fg or gf, because it is going to be g after f. And that's going to be compose arrows. And we will take g after f. Oops. Or f after g. Okay. So now if we call gf and we put in true, we get back nothing. Still get back nothing. All right, hold on. So we take this. Oh, because it's a function. People need to call their functions. And then we put this back to gf. And we still have a problem. So f will take a bool to a string. Yes. Hold on, there might be something wrong with this. All right, so for our compose arrows, what we want to do is take our y, that's then going to map the x, yeah, and then if y has length, we extract it or we return Yeah. Yeah, yeah, yeah. Oh. I'm a silly goose. All right. So we want this to happen after. So this would be GF. I thought that would work. All right. Oh my gosh, so silly. Let's see what's going on here. So we define our arrows, we compose our arrow, and we call GF with true. So when we send in G is going to be, doesn't matter. The first thing we're going to do is F on that. So the first function is going to be F. And we're going to take our Boolean, and then we're going to return the string. Okay? And that's going to be true or false. Then with G, we're going to map that function. What are you doing wrong here? All right, this is super silly. Hey, Daniel. You missed a little bit. Nothing too crazy. When did you leave? Okay, so let's see here. This is pretty interesting. Let's see what's going on. So we get our F after calling that, and that's going to get us back an array. Okay. So let's do that. So we're going to call F, which is the first one, right? And then F is going to be that arrow that goes from Boolean to string. So now let's see if there's a problem there. Oops. Let's see here. Sorry about this. This is super embarrassing. Well, let's make this just string. Okay. So it's something to do with our upper string. So we want to check to see. Oh, goodness gracious. I am such a dork. It was doing exactly what we told it to do. So I'm already seeing a problem with this type of programming. We'll have to have. Anyway, so if we do that, we want to do to uppercase basically. And it'll check to see if it exists. All right, so now if we do upper string. Okay, so then that's good. But what if this didn't do that, right? What if this did to lowercase, right? So this would be a invalid definition. Ooh, there's something in there. An error should also go, right? To lowercase. And we want to say is equal to X. Strictly equal to X. Okay, so that's not strictly equal. But if we, let's see what happens here. There's something else we need to do, right? So there was an error in there. So now let's go down to define arrow. And what we need to do here is a try catch. So we'll do try, because if it's invalid, we don't want invalid stuff to run in there. So we'll do try, and we'll do this. And inside of here, we need to do a catch, and we'll catch with E. And here we'll just return empty. Boom. So now we've actually accounted for exceptions. So we still can only run valid stuff inside of our context. Okay, so that gets rid of the errors. That does all that. We have a mapping now for those morphisms. All right, so since this doesn't work, the only way this would work is the to uppercase. Okay, so yeah, so now we can compose things in there. And just to check, let's do a const, and we'll say toString, and toString will be this function. We need to make sure that a mapping or a composition in there matches a composition there. So we'll say, we'll just call that toString. And this is why I have a hard time proving this to be a functor. You'll see why here. So I got to figure out a way around this. And then I might be able to come up with a proof. But right now it's about to just be horrible. All right. So now say we do something else called toUpper. All right. And toUpper is basically this function. Okay. Oops. Okay. So now we get back our true, we get back that. So let's do compt is equal to, and let's do compose, and we'll compose, what is it? F after G. So F is toString. Or G after F. So the first thing we do is toString and then toUpper. Okay. So now this is where everything breaks down for this. And I got to figure out a way around it. So now I have this composed function that's going to be that. If I run comp with true, I get back the same thing, right? But if I run comp with, say, null, it maps to false. That is not what it maps to inside of our little functor, because we don't, well, inside of our little context. And that's why this isn't a functor, in case you're wondering like why I'm having a hard time. So what I need to do is come up with a way to isolate that and get that to map. But that is the one thing. And it's funny because I've been going through like many ADT definitions and things. And there's a lot of things that don't make them functors, but I mean, we still use them every day, but goodness gracious, it would be really nice to be able to do this. So doing null, I would need to have to, well, no, because this is invalid. Maybe that's right. See, that's why I have a hard time proving this stuff. How long? Okay, so I don't know. This has been kind of a fun little experiment that I've been playing with. I've been working on videos. I'm going to be releasing them starting soon, along with some additional content and things, where I actually like draw out the examples. Here, let me show this again. So it'd be basically doing like the silly drawings like this, except it would be with my Wacom tablet and stuff. And then showing all that silly stuff, explaining what the notation means, and writing commuting diagrams, and then using a system like this to be able to show like, oh yeah, we didn't even show isomorphisms. So that was the other thing I learned from going through and doing this, is how rare an isomorphism is. Because to be an isomorphism, you have to be bijective. So remember, to be injective, the S has to be, or to be injective, as it says here, right? Injective, for every T belonging to T anyway, it has an implication. But the cardinality of your source must be less than or equal to the cardinality of your target. So the surjection is the other way around, which means the cardinality for a bijection, since it can't be less than and it can't be greater than, it has to be equal, right? Like So for there to be an actual isomorphism, the cardinality of both your source and your target must be equal for there to exist one. Well, and oh hey, and W, it's not really the type system. It's more the mapping of objects, like thinking of the different subsets. So when I first started this, I was thinking of how I've been thinking about JavaScript poorly. Let me show. You can watch that. But anyway, it's mostly long story short. If we think of when we're running things, instead of having all these types, like we want it to be from a string to something, but really we have one major type called JavaScript values, right? And then that's where these types of system where we can create these subsets of them. And then getting those subsets as types or objects inside of like the category of JavaScript. We can then, what I'm trying to do is create how to actually create a functor. So even though I want to think of it as types, I don't really want to. I want to think of it as subsets of a much larger type. And then it's easier to do the diagrams that way, right? The only problem is, well, and that's where not your bottoms, but like your invalid stuff comes into play. Because because we can pass any value of anything to anything, right? So we're really just going from type of JavaScript values to JavaScript values, and no matter what, we're always returning a type of JavaScript values. So I don't know. I'm not very smart at this stuff, and I'm not really good at explaining it either. But hopefully with the diagrams and being able to show this. But anyway, so if you think about how, sorry, I got derailed there. So if you think about how rare an isomorphism is in our everyday life, like that's crazy, because that condition has to hold true, that the source has to match the target in cardinality. Like they have to be the same size in order to get back and forth, right? Because if you think about it, to be bijective, not only there must be a unique value for each one of those sources, it needs to point to a unique value in the targets, but it needs to have full coverage in the target, which means for every single T, there needs to be a source. For every T, there needs to be an S, so it can go back to it. And that's just insane to me. Like, it blows my mind how rare those really are. Like, outside of identity, think about it. Like, that's insane. They are so rare. And then it's funny because if you think about it, what is the difference? So I have this Boolean here, right? So what if I were to create a set called 2, right? And it's basically just a set that has 2 elements in it. So I can do define set. And then I'll just say 1 and 2. Heck, these are the labels that I'm giving 2. And this is my type of 2, right? Like, so what would a mapping like this look like? And we can get rid of all this crap because we can show an isomorphism here. We can get rid of all of this stuff. All right, so like think about this. This is insane to me. And I'm really glad I went over and started like rereading all these books and like really drawing them out and trying to fully understand like what's going on inside of a set. So if I were to take a function, so we'll say 2, and we'll call this define arrow, and define arrow will go from bool to true. True. I'm sorry, to 2. Okay? And this arrow is going to be a defined map. Well, no, this is going from bool to 2. So this arrow or this function will basically just be x. And if x is true, because it's going to check to see if it's Boolean, then we just return 1. Okay? If x, return 1. Otherwise, return 2. Right? So now we have a mapping. the only thing we can do with this is, since it's a Boolean, it's going to be true. If it's true, we map it to 1. Otherwise, we don't, right? So now we do from. And here we can do define arrow. Or actually, let's do define map here, because we want to do, if I have a 1, then give me a true. And if I have a 2, give me a false. So check this out, right? If I go 2, and first of all, if I pass nothing in of not a valid value, 2 goes from Boolean to a 2. If I pass in true, I get 1. If I pass in false, I get 2, right? So what happens when I do from? With from, if I pass in 1, I get true. If I pass in 2, I get false. They're the same thing. Like, this is what it means, like, for an isomorphism. When people say unique up to a, or it's equivalent up to a unique isomorphism, this is what they're talking about, at least in set, right? This is one of the things they're talking about. This is actually, I can represent Boolean as any 2-element set, as long as I can create an isomorphism, or as long as there exists an isomorphism. So for instance, now we can compose these 2 arrows, and it doesn't matter where I start, compose, and then we do our 2, and we do from, and what is compose arrow. So we'll call this comp, so we'll do const, and we'll call this comp, just for the compose, and we'll do compose arrow, to and from, and then we do comp, sorry, and it needs to be arrows. Okay, so then we do comp, and we're starting on 2, so that's going to be a Boolean. If I put in true, I get Bumpkus. Hold on. Cannot read property map of undefined. Wait a minute. Something is amiss. Hold on. So, wait. This is what happens when you're like, I'm just going to build a bunch of stuff. So why is that becoming... So 2 is... Oh, sorry. But that shouldn't have happened. That shouldn't have happened. Curious why that happened. All right, hold on. I'm so sorry about this. Ugh, it's ridiculous. All right, so we take our arrows. I'm probably doing something so silly with these arrows. We take our arrows. Our 2 is an arrow that goes from bool to 2. We have our defined set. Okay, so that goes to a 2. All right, so it's something with this composition. All right, hold on. I'll figure this out. All right, so then we do our map. All right, F and G. See, it shouldn't have arrowed the, or arrowed. Ha! It shouldn't have errored. So this is arrowing. So hard to say. So if we take our Y, we want to be able to unwrap our Y. So we take our X, and then we map it. So Y, oh Y, is that coming back? So we take our f, which is from. Hold on, maybe this will tell me. All right, line 5, let's just do a console.cry for x. That's a 1. So when it came back from that x, oh, that's fine. Let's see what f of x is. Sorry about this. All right, so f of x is true. So that came back true, but it did not wrap it. Why did it not wrap it? Why did that not wrap it? That should have given me a... Oh, I'm so sorry. I am so sorry. The reason why I didn't is I didn't define this as an arrow. My bad. Okay, so this is going to be an arrow that goes from 2 to bool. All right. I am so sorry about that. That is ridiculous. I'm like, hey, check out this neat thing. And then I'm like, screw that. Okay. So now that we have that composition, we'll notice, and again, I'm just trying to show isomorphism here. If I put in a 3, of course, I get back nothing. If I put in a 2, I'll get back a 2. So we can do this the other way with from and to. And if I start at one area and I come back to the other one, I can get back no matter what, no matter where I start, I'll get back to where I went to. So I never really understood. I mean, I understood what unique up to isomorphism meant and like why that was equivalent. But now playing with sets and things, I'm really starting to see like, yeah, it's kind of a lax condition, but inside the context of all of this, it's really not that laxed. I mean, it's not that far from being equals. Like, I mean, it really isn't if you think about it. I mean, these two things, even though they're completely different, they're actually the same. As long as there's an isomorphism, I can treat any one that same way. So here, if I do true, I'll get back to true. Right? If I put false, I'll get back to false. And they're so rare, like because they have to equal each other. So anyway, that's all I have. We didn't really get into equivalence stuff. But now that I have this system, like we can define things like product types and actually show like why the universal property of a product type in JavaScript, like being able to create pairs and things like that, like why that is the best function and how to do that. And other things like we can learn how to use the fact that there is a universal property, like actually exploit that to create relationships between things. It's really interesting. So, and again, just to recap, like one of the other things I really thought about, and again, I'm sad with equivalence relationships, is it allows you to set up these cool partitions. And instead of using functions to just modify stuff, we can use functions to actually clarify stuff, you know, or not clarify, but classify. So if two different values in a set, when going through a function, if both of them map to the same value, we can use that for classification. Like, it's insane. But anyway, this is just some of the stuff I've been playing with lately. I've been recording. I have about 4 of them done right now. But basically where I go through and draw out the maths and then like draw the pretty little pictures and the bubble diagrams with the arrows pointing at things and like what a product type is and projections and all that stuff. I have a lot of those there and I basically bring them in and show examples like this, like how to create intersections, like actually work with sets. So I guess be looking out for those. I don't know. I just wanted to nerd out. This is some of the stuff that I do off camera. Like I mean, I do React at work and things like that, but for fun, I don't really like sit and build to do apps and things like that. I try to like kind of, I don't know, do stuff like this and figure out how to make sense of it. And I don't know, I'm determined to show that JavaScript is a capable functional language, like despite what people call a shortcoming. And what really got me, there was the guy that wrote this book. I can have Spivak. I can't say his name, and I haven't heard it pronounced, and I feel so bad. But I was watching a lecture he did, and he blew my mind with something. He's talking about adjunctions. He's talking about adjunctions, and he's talking about free and forgetful functors and how they work. And he got me thinking because he was showing like the adjunctions left and right, like L being a left adjunction to set into partial sets, like where they're all sets are the objects, but their morphisms are partial functions. We use full functions, right? Like everything maps to something. Like for every input with that rule that I gave at the beginning, this one right here, for all S's belonging to S, with S being a source and T being a target. For all S's belonging to S, there exists a T belonging to T, where F of S is equal to T. Anyway, but there are ones to where that's not true. It's not for all. Yeah. Oh, thanks, Joseph. I appreciate that. Oh, all kinds of people were in here. I'm sorry. Yeah, I don't know. This is just some stuff I've been thinking about. Wanted to kind of lay it out, I guess. Have a nerd session. I haven't really geeked out on camera in a while. So coming up a little over an hour and a half, I guess we'll call it. I just been going on and on and on. I don't know. I do this every Tuesday at 6:30. Sometimes I work on React stuff. I'm going to be doing more of this. Just nerding out, playing with things. I want to show like how to do pre-images and pullbacks. Like they're really cool. And they're great when you learn like equivalence relationships. But I don't know. They don't really fit into general. They're cool to understand, like how functions and all that work together and kind of give you a new view on it. But I haven't found too many like practical uses for them yet. But oh my gosh. So the book is Yuri said, could you please repeat the author's name? It's actually, I'm getting all this from a lot of books. This is one of them. David I. Spivak, Spivak. It's Category Theory for the Sciences. I'm also doing another one from him called, I've read through them. I'm going through and actually like going through everything detailed, like really making sure I understand every sentence and every part, especially around set. But I'm doing that one. I'm doing another one called Gentle Introduction, Category Theory, A Gentle Introduction. You can search for that. The other one by him and I think Brandon Fong is 7 Sketches of Compositionality. Going through that one. That one is blowing my mind with partial orders and stuff. Just in that first chapter, it gets crazy before, but a lot of it is just material. I like the approach on that one. I'm also, what's another one I'm reading? That one. I'm just looking mostly at like these old books. Like I have a bunch of these old books from like the 60s on like finite mathematics, things like that. But yeah, a lot of great resources out there. So anyway, that's all I have. If you guys like this, I don't know. Thank you. If you don't, please let me know what you didn't like about it, and I can adjust and make something you like. Goodness gracious. Yeah, that's all I have. Thank you so much for joining me. I do appreciate it, and I'll see you again next week. Have a wonderful week.